Perfect. Thank you. Hi, everyone. My name is Trevor, and I'm a PhD student at Simon Fraser University. And I'll be talking today about my project on near-term emission targets need immediate attention in the USA. And this is a application of PyPSA-USA sector. So a lot of my research can be motivated by this graph that is shown here. So in 2015, at the Paris Agreement, the USA pledged to get 50 to 52% of reduction in emissions from 2005 levels by the year 2030. The historical trend in relation to 2005 levels is shown by the black line, and then the dark blue and green lines show the policy targets as of 2024. So the reductions that still needed to hit this 50 to 52% reduction, with the dashed lines showing the last 5, 10, and 15-year trends. Emissions don't follow linear trends. However, I think this graph is just really representative of significant changes are needed to the current decarbonization solutions to get this aggressive decarbonization that the USA has pledged. So this kind of motivated my research question of what high impact options exist today in the USA to make aggressive decarbonization progress by 2030. To answer this, I mapped out my requirements. So optimization model with full USA coverage. I needed it to be sectorally explicit. And that's because a lot of supply side electrical solutions, just based on timeframes, aren't really suitable for 2030 anymore. The result metrics I want to look at are primarily emissions and then marginal energy costs, as if a solution has negative impacts on the ratepayer costs, that's not great. And then academic projects, so trying to keep open science as possible. To target the high impact options, I use global sensitivity analysis. The formal definition is it's the study of how uncertainty in the output of a model can be apportioned to different sources of uncertainty in the model inputs. More informally, it's more how do changes in input uncertainty map to changes in output uncertainty. Part of the GSA you get, GSA being global sensitivity analysis, is you get a sensitivity index, and this basically says what the impact is of a input uncertainty on the output. So it allows you to rank different input uncertainties. And then some challenges to address with GSA, just the data collection, result parsing, and computationally expensive nature of it. So this led me to use PyPSA-USA, which I'm a core developer on, open source data and planning model of the USA. With this project, we overlaid a lot of sector additions on it. So that includes modeling the natural gas in detail, breaking out the residential, commercial, industrial, and transportation sector, and adding in end-use fuels such as heating and cooling. These kind of sector additions that a lot of inspiration has come from PyPSA Europe. For the actual process, we run each state individually. So there's 48 different model runs. We apply a GSA to each state. We identify the high impact drivers on marginal costs and emissions. And then we do a more detailed uncertainty propagation just via a Monte Carlo analysis on those high impact options. And with that, I will jump into some of our results. So the first claim I will make is that marginal energy costs can be kept low, but they're very sensitive to fossil fuel prices and portfolio standards. How I'm arriving at that is based a lot off of this chart. So what this shows is the GSA results, and in relation to average marginal energy cost, yearly marginal energy costs at a per state level. So how to interpret this is each state, whatever the parameter is color-coded, that's the first, second, and third most impactful on input uncertainty on average annual marginal energy costs. For example, natural gas export costs, so how much a single state makes by selling natural gas to a neighboring state or region, such as Canada or Mexico, is generally the most impactful uncertain parameter on average annual marginal energy costs across the USA. Moreover, the import cost, so how much states are buying natural gas at, is also very impactful. And this paired with some other results, we can kind of arrive at the conclusion that ensuring that you manage your natural gas price uncertainty in a nation like the USA, which is so heavily invested in natural gas, becomes super critical to ensure marginal costs do not get out of hand. Another interesting finding from this is the renewable portfolio standard, which is actually the most impactful parameter on marginal energy costs in 7 states. And I thought this was kind of interesting. And if you go and explore this a little bit more, and our uncertainty propagation stage, we can create these box and whisker plots. Those 7 states, they all map to the states with the highest level of uncertainty as well, or highest range of marginal cost output. So even though fossil fuel prices are generally more impactful across the nation, states that have aggressive RPS standards, renewable portfolio standards, their marginal costs can get way higher than just fossil fuel uncertainty. And where this comes from, we can look at California, which gives a good example. So in this chart, I'm showing California during our uncertainty propagation phase, renewable portfolio standard uncertainty in the bottom, so no policy all the way up to full policy for 2030, and then our y-axis is marginal costs. You get these like different regimes where like RPS is not binding for a lot of the runs, so costs can be quite kept low. Then RPS starts to bind on the solution. However, the model does have fairly good options to balance that out to ensure costs don't get astronomical. And then you have this last regime where the model starts implementing really funky solutions just to satisfy the RPS constraint. And those solutions are very expensive. And that's where you get this extreme outlier. So ensuring that you pair portfolio standards with other system investment pathways in appropriate timelines becomes really important to manage costs. The next claim I'll make is that methane uncertainty is key to manage emissions, and I guess the climate impact emissions. And again, we'll look at a sensitivity analysis kind of hex plot here. And this is now showing total emission sensitivity. So what parameters influence carbon and methane results the most? So carbon and methane summed together. Green is showing your global warming potential value. So this is the CO2e value I attach to methane leakage. That is overwhelmingly the most impactful parameter when you're measuring total carbon results. And that kind of makes sense because this value is it has a pretty big range. It can go from like 20 if you're doing like 100-year potential all the way up to like 80 if you're doing a 20-year potential. And that's purely a modeler's choice, but you have to be really aware of that when looking at carbon impacts. More interestingly is the purple and red results, which are upstream and downstream methane leakage rates. And particularly upstream methane leakage rates, these have very actionable solutions, which is if regulation comes in and states that all equipment by natural gas producers has to operate given certain leakage rates, the equipment is designed to have very low leakage rates. It's just right now there's no regulation that really states that, so the uncertainty on that can really get out of hand and cause really high emissions. And the last point I'll highlight here is that results are really regionally interdependent. And I'll do a quick case study with Ohio and Indiana. So Ohio here, if we plot our natural gas export costs along the X and our marginal costs along the Y, we can see that with a higher export cost, so they get more money from selling natural gas, their marginal costs go down. And in neighboring Indiana, if we plot their import cost, so a higher import cost means they pay more for natural gas, their marginal costs generally go up. So you kind of get this one state winning, one state losing kind of dynamic. And this is not like a novel result. I know lots of other literature states this as well. However, I think this just paints it really clearly that ensuring that states work together at larger regions to maximize social welfare is really important. So you don't have winners and losers. And just in my last 30 seconds, I will highlight some conclusions. So managing fossil price fuel uncertainty is really important. Portfolio standards have to be planned with other system expansion. Upstream methane leaks need to be regulated. Results not shown here, service sector heating and light-duty electric vehicles are high impact options in the near term for carbon reduction. And this is entirely open data and open source. So there is a dashboard available if you want to go and investigate all the results at PyPSA-USA.gsa.com. And all the result figures here came from that dashboard. But with that, that is all I have. Thank you very much.
Thank you, Trevor, for that very interesting talk about PyPSA USA. So, we just have a single question at the chat box. If you have a question, you can send it on the chat box. So, the first one coming from Tom: how are export cost versus import cost model?
Yeah, so each state has capacity constrained natural gas pipelines to all adjacent regions. There are also flow constraint uncertainties on there as well. So I'll look at how much each state trades with the neighboring state historically, and I'll make sure to bound that. And then based on that, the states can trade as little or much as they want to within those bounds. And for each unit they trade, they either make money or lose money. So if they're exporting, that's just a negative value applied to the objective cost. So just like a negative marginal cost in the link. Yeah, thank you.
Okay,
That's a good question.
thank you. I hope that answers the question. Oh, well, there's a request for a publication or preprint. Maybe you can send it on the chat later. Maybe
Yes.
one last question coming from Nathan. How is Canada represented in the model?
Yeah, so Canada is not in the model. However, there are trade links in the model. So between each state and each province in the model, we pull out both natural gas and electricity trade values. And then similar to the natural gas values, those are capacity constrained and energy constrained. And the energy constraints are a certain parameter, and each of those have prices as well that are uncertain and included in the GSA. And that's for Canada and Mexico. Mhm.
Okay,